Right, so gamma ray bursts. What are they all about? Well, the story goes back to the 1960s and the Cold War, actually, and the monitoring of the Partial Test Ban Treaty. The Americans and Russians agreed this Partial Test Ban Treaty to ban atmospheric atomic tests. And in order to monitor it, the Americans decided they would launch a series of special satellites called the Vela satellites that were looking down at the Earth and were looking for any of the high energy gamma rays associated with the explosion of a nuclear device. And if they saw them, they would report back and report the timing of them. And with a cluster of them up there, the differential timing between the arrival of the pulse at different sites could allow the Americans to triangulate back to work out whereabouts they had come from. That was the idea anyway. And you can see a little artist's impression there of one of the Vela satellites. They launched quite a few of them, fairly simple beasts with covered in solar panels and that icosahedral shape, but with a gamma ray detector pointing down towards the Earth. And then in 1967, on the 2nd of July, the Vela 3 and 4 satellite group that were up at the time detected the first gamma ray flash. And this initially caused a bit of a stir in the American intelligence community, thinking that somebody had set off a nuclear weapon when they shouldn't have been doing so. But they soon realized that the shape of the pulse of gamma rays didn't seem to match that of any known type of nuclear weapon. And they fairly quickly dismissed it as such and filed it away under curiosity. And gradually over time, more and more of these flashes were seen. In fact, they started building up a map and realized they were coming not from objects on the ground, but from all over the sky. And so by the 1973 timeframe, they actually got round to publishing a paper in the Astrophysical Journal, alerting the normal scientific community to this phenomenon that had been observed by the intelligence people, and publishing this map showing the location and intensity of all of these strange gamma ray flashes that they were seeing all over the sky. And numerous people started putting forward different possible explanations for this, from colliding comets to neutron stars to quasars, all sorts of things. But as time went on, we got to 1979 and a very famous incident occurred, the Vela Incident, which sounds like the title of a bad 1970s sci-fi movie. But it was again one of these Vela satellites detected a signal from the ground, and you can see the graphs there showing it. Now this doesn't look like a gamma ray burst. This does look like the characteristic pulse from a nuclear weapon, and let me explain why. It's a double pulse. What happens with the gamma ray bursts is you get a flash of gamma rays that brightens and then fades away. But with the nuclear weapon, what happens is you get the initial flash from the initiation of the explosion, and then the region around the expanding nuclear fireball becomes opaque to gamma rays and scatters them in every direction and reabsorbs them for a while until it dissipates, and then you get the second pulse releasing the gamma rays back out of the cooling fireball. It becomes transparent to gamma rays again, and so you always get this double flash. Now that's what I meant when I said that the initial observations didn't see anything that looked like a standard nuclear weapon, because they didn't see this characteristic two-humped trace for the intensity of the gamma rays. But in 1979, they surely did. They saw this double flash characteristic of a nuclear bomb. And the Arecibo Radio Observatory also detected the radio pulse from it, from whatever this event was. And for a long time, people were arguing about it, but they were able to trace the site of it to be Prince Edward Island, which is shown here as the red dot on the map. Now, this is off the coast, thousands of miles off the coast of South Africa. This is the southern tip of Africa here, with Cape Town about there. So way off in the middle of nowhere on this little island, Prince Edward Island, almost all the way to Antarctica. This is Madagascar here. And for a very long time, that people speculated about what this might be, and no one was admitting anything. One possibility was that it was some sort of freak asteroid coming in from outer space and detonating or exploding in the atmosphere. But again, no one could really account for the double flash. It was even speculated that it might have been an asteroid made of antimatter that would have perhaps caused a nuclear explosion. But recently, they've managed to identify that there were indeed a pulse of the characteristic iodine-131 isotope found in Australian sheep a few years after the event. And this is a dead giveaway that it was in fact an ordinary uranium nuclear weapon. And the theory goes that it was actually an undeclared nuclear test. There was a collaboration between South Africa, who provided the facilities, and Israel, who provided the bomb, using material that they'd borrowed from the Americans, shall we say. I think they stole it, actually. So from 1997, though, we started to be able to use better satellites and better telescopes and be able to begin the process of identifying where these flashes were on the sky with a greater degree of accuracy. And the Beppo-Sachs satellite, pictured here, managed to catch the X-rays, which come as a secondary flash after the gamma rays have died down in GRBs. And together with the William Herschel telescope, they managed to also find the optical afterglow of the event. Now that was excellent, because they were able to measure the power, apparent brightness, and also look at the redshift from the optical spectrum and get the distance from the redshift based on the expansion of the universe, and realized that the distance was immense. It was halfway across the visible universe, and therefore the power output of the event itself must be tremendous. This was an absolutely enormously bright object, to be seen as bright as it appeared at that distance. And that was followed up by an even better pinning down of an event in 1998. Supernova 1998 BW occurred in a galaxy 140 million light years away, just one day after a gamma ray burst had been tracked to the same location. And this was the first time that we were really able to provide this linkage between gamma ray bursts and supernovae. And they even were able to track back and look at photographs of the galaxy in high resolution from before the event, and figured out that there was a large star there, 25 to 40 solar masses, so a real whopper. And so this was a clue that the whole thing probably had something to do with the supernova detonation of this very massive star. Now, just as an aside, we'll just go back and have a little refresher on where stars get their energy and what happens to them in their life cycle. So for an ordinary star, once the temperature in the core, due to the crushing pressure of gravity, reaches a point where you get to 10 million degrees, that's hot enough for nuclear fusion to begin, as shown in the diagram. The ordinary first few steps from hydrogen on the left here, fusing together to make the heavy isotope of hydrogen, deuterium, to make helium in form of helium-3, and then on to helium-4. And that's the normal process that drives most what we call ordinary or main sequence stars. They are converting hydrogen to helium and releasing energy along the way. But in massive stars, the temperature in the middle can go up way beyond that 10 million degree ignition point and get up to hundreds or even billions of degrees. And that is hot enough to cause further rounds of element generation and consumption. And so for a moderately massive star that was perhaps 20 solar masses, you would get hydrogen being burned, as we say, to helium, and that would be likely to last at about 7 million years. And then the helium will start burning itself and give the star another 500,000 years as the helium is converted to carbon. The carbon will be consumed over a period of 600 years to give us neon and indeed some oxygen as well. And then the neon can be burned to further elements for a year, and the oxygen give it another 6 months. And by this stage, you've created silicon. And you can burn silicon and form iron, and you get one more day of life for your star out of that process. But at the end of that, your star has run out of options and run out of luck, and it will explode. And the reason being that the source of energy in the center gets suddenly switched off, because iron can't be converted to heavier elements and release energy in the process. It actually consumes energy to go any further, and therefore suddenly the core cools down and can't support the overlying crushing pressure of all of the outer layers, so they implode and crush the middle down. Now, this process occurs for stars that are over 10.5 solar masses. In fact, anything below 10.5, and they stop at the silicon neon sort of stage, and they end up as oxygen, neon, magnesium, silicon, white dwarf stars, if they're between 8 and 10.5 solar masses. So that makes white dwarfs. But over 10.5 solar masses, they will go on and try and build an iron core, and then they will explode as a supernova. In fact, they build the next element up. They do build nickel, but they build a radioactive form of nickel called nickel-60, which soon decays back to iron. So that's actually the end stage there. But of course, they blow up spectacularly when this implosion occurs and collides with what it forms in the center, which will probably be, for a modestly giant star, it'll be a neutron star, as has happened here in the Crab Nebula. And a neutron star, this is an artist's impression, would be about the size of a city, but contain perhaps 1 or 2 solar masses of material crushed down to a density where you have the same density as an atomic nucleus, because it's just a ball of neutrons covered by a thin crust of other material. And these things will form as long as your star is less than about 20 solar masses. So in that 10.5 to 20 range, you'll get a neutron star. If the star was bigger than 20 solar masses, then it will try and form a neutron star, but the resulting central dense core will exceed the 2.5 solar mass limit, called the Tolman-Oppenheimer-Volkoff limit, which is the maximum mass for a neutron star. They can't support themselves the strength of the neutron matter, if you like, is exceeded by the pressure of gravity, at which point the whole thing then, so the story goes, collapses down to a black hole. Now that's the simplified life cycle of giant stars in one go, but it explains that we get one of two outcomes, either a neutron star or a black hole. Actually, things are a little more complicated. That's the subject for a different talk, though. Now, in 2004, to go back to the gamma ray story, the SWIFT satellite was launched, and this is an excellent tool. It can detect gamma rays from anywhere on the sky and then pivot on its axis and slew and lock onto the target and pick up the X-ray and optical components of the explosions, and also alert the rest of the astronomical community down on Earth so that other instruments can be rapidly brought into play. And what this enabled was them to catch the gamma ray bursts very early on in their life, within seconds or even fractions of a second of their initiation. And so we've now been able to construct quite a lot of light curves for different gamma ray bursts. And you've got a selection of them here. You can see that time going along the bottom and the brightness going up the side, and they're quite complicated. You look at this and you initially think, gosh, they're all over the place. There's single bursts like this one, or this one, or this one, or this one. And then there's ones with multiple peaks, double peaks, and really complicated structures. And it's quite daunting to sort of look at all of that. But if you study it a bit more closely, you notice that the timescale along the bottom is not the same for all of them. Some of them we're going from the sort of just before the explosion, like -2 seconds, to 40 seconds, 80 seconds, 20, 60. Others are much shorter. This one's only going to 5, and the peak was very narrow. Again, very narrow here. And so fairly soon they were able to classify these into 2 groups. You could divide them into short gamma ray bursts that had a peak lasting from milliseconds to seconds, and then there were long duration gamma ray bursts that last tens of seconds to tens of minutes even. And this is very suggestive that there were 2 different processes at work. Now, short gamma ray bursts, if we take a look at those first, up to about 2 seconds in duration, about 30% of the categorized gamma ray bursts were classed as short, and they were mostly found to be coming from the environs of giant elliptical galaxies. I think this is one going off here in this large elliptical galaxy. And large elliptical galaxies are regions that are full of yellow, orange, and red stars that are all dwarf-sized and small and long-lived. And the reason is that there's very little gas and dust left in these galaxies. It's all been consumed into stars, so they're quite aged galaxies. And as a result of that age, all of the very big and bright stars have exploded in the 10 to 20 million years of their short lives for giant stars. They've become a supernova and are no longer shining. So they're no longer any white stars or any blue-white super hot stars in these galaxies. And there are no new stars being formed. So this is interesting. This tells us that these gamma ray bursts can't really be associated with the death of giant stars, because there just aren't any anymore in these galaxies. These GRBs in giant elliptical galaxies are associated with a galaxy where the stars are old age. Now, the other clue is the fact that they are short duration. And whenever an event is of a short duration, it must come from a small region of space. It's just not possible to have a single event that occurs and is coordinated over a large region of space in a very short time. And the limit is the speed of light, because whatever it is that is the trigger, be it at one edge or, as in the diagram here, in the core, if the trigger is in the core, it can only be known that the trigger event has occurred after the passage of enough time for a beam of light to have arrived at the outside edges. And so if your event lasts, say, 0.2 seconds, as you might get for a short duration gamma ray burst, then the whole region that is involved in that event must be less than 0.2 light seconds in radius. That's around 60,000 kilometers, so a quarter of the way between the Earth and the Moon. So it means these things must be small. And, well, small we would associate with very compressed dense objects, so white dwarf stars, neutron stars, or black holes, because ordinary stars are way too big for that sort of duration event. Now, we know that the merger of two white dwarf stars, or the explosion of one white dwarf star due to extra added material, gives us a type 1a supernova, and those have very specific characteristics that don't match those of gamma ray bursts. So we can probably rule out white dwarfs. We also know that mergers of black holes give gravity waves, but no bright flash. We've recently detected the merger of some black holes by gravity waves, but there was no optical component to it at all. So it's probably not something like that, which leaves us with neutron stars. And indeed, you won't be surprised to know that this has been confirmed. They've detected a spiraling in collision of a pair of neutron stars. The neutron stars orbit each other, and because this process starts to result in them getting quite close to each other, they start to give off quite intense amounts of energy by gravity waves, and these gravity waves carrying energy and angular momentum away from the system means that the orbits have to fall inwards to provide that energy, and so the neutron stars spiral in towards each other until, of course, they touch, at which point their total mass exceeds that Tolman-Oppenheimer-Volkov limit, and they are forced to detonate in a huge explosion. And we call those explosions kilonovas. And the result of a colliding pair of neutron stars is a kilonova. It's very interesting. It was recently discovered that the massive release of neutrons that occur when this disruption event happens is the source of more than half of the heavy elements in the universe, the lead, the gold, and the uranium, and so on. All the really heavy elements are formed by the intense bombardment of neutrons from colliding pairs of neutron stars. So the life cycle here is that you have two very massive stars, and eventually first one and then the other blows up as a supernova, leaving a pair of neutron stars orbiting around each other, much as the original stars did. But eventually the radiation of gravity waves forces them to collide. And so we think that these short duration gamma ray bursts are associated with the collision of these neutron stars, or these kilonova explosions, as we call them. And we think that, as shown in this diagram, when it happens, you can get a jet formed along the rotation axis of the spin of the spiral, and material shot out along the jet can be very, very intense And if you're looking down that beam, because it just happens to be pointing towards you, that's when you see a gamma ray burst. Whereas if you are off axis out of the beam, then we see an ordinary kilonova explosion. What about the 70% of long duration gamma ray bursts then? Well, long duration means the objects have to be larger by that speed of light rule, and they have to be of the order of light minutes. And that's probably pointing towards supergiant stars, things like Betelgeuse and Antares, and some of the real whoppers like the Pistol star, with 50 to 100 solar masses. And we also, turns out that we can track these, and most of these long duration gamma ray bursts turn out to be within spiral galaxies that have active star forming regions in them that are of course rich in young giant stars. And I repeat, there are no old giant stars in the same way that there are no old bold pilots. They just don't exist. This all points, of course, to the normal core collapse supernovae that we were talking about and the death of a giant star. And so the theory goes that these stars, the very largest classes of stars that explode, so well over 20 solar masses, are what gives rise to the long duration gamma ray bursts. A very pretty diagram here of the evolutionary curve of a giant star gradually starting with hydrogen and adopting that onion-like structure as it builds all the elements through to its iron core, and then exploding outwards and forming a very violent destructive outcome with a very powerful jet out of it. Now, exactly the details of what's going on there are quite interesting, because inside this massive envelope of this giant star, the iron core collapses, and over 20 solar masses, it forms a black hole. And so what you have is a black hole in the middle of the dying star, but still surrounded by all of those outer layers. And instead of, when you form a neutron star, the material falling inwards because it's now unsupported until it collides with the very solid and rigid crust of the neutron star, and then rebounding outwards in a shockwave that blows the rest of the star apart, i.e. a core collapse supernova. If these things collapse directly to a black hole, then there is nothing to rebound from. And so the material can fall inwards directly into the black hole and feed it, make it larger and larger, except for the fact that these things are spinning. They're always rotating. There's always some net spin on everything in the universe, so it seems. And so they can't fall directly straight in, or not much of the matter can. So it ends up forming a swirling accretion disk. And so what you get very soon after the collapse of the core is a black hole with an accretion disk spinning around it, feeding matter into the black hole, that also generates an enormous high temperatures because of the friction in the disk, and a very complex and twisted magnetic field that forces these jets to form. But this is all happening inside the star, which the outside layers haven't really noticed yet, that all of this portents of doom has occurred in the middle. And so what happens is you get the jets from the rapidly accreting black hole spinning away inside the center of this parent star. And the jets force their way out and blast holes through the polar regions. And then the enormous release of energy from the accretion disk also starts to tear the mid part of the star to shreds. And so you get this absolutely enormous explosion from the inside out as all of this energy is released. Now, black holes and accretion disks are actually almost the most efficient releasers of energy of any process. I think nuclear fusion releases about 1% of the mass energy, according to E equals mc squared, of the nuclear fuel that it consumes. So it doesn't even consume the whole of the star. It's actually quite inefficient in those terms. But a black hole accretion disk releases 20% of the mass energy in the form of radiation and gravity waves and neutrinos and everything else. And so it's hugely more efficient at releasing energy. And so these things are phenomenally powerful. So the idea, if you can kind of imagine it, is you have this black hole engine inside the star to begin with, which eats the star from the inside outwards and forces a shock wave of ever expanding power outwards through the star, along with the jets that are carving their way out. And it creates a jet in both the spin axes, with shock waves traveling along the jet that can superheat the matter and accelerate the particles very much as we do in our particle accelerators here on Earth. So there's a sort of animation of it here, of the black hole growing and eating the star in the center, and these enormously powerful jets acting like particle accelerators, producing these tightly collimated beams. So those jets are what we see if we happen to be unlucky enough to be within the beam, within 2 to 20 degrees of the direct view straight down the axis. Then we'll see the vast amount of energy that comes out in the beam, and that is when we get the gamma ray burst from these objects. Of course, most of them miss us. There's a lot more directions that you could point these things in that won't hit the Earth than there are that do. So we see some of these hypernovae, as we would call them, that are direct collapse to a black hole as very powerful supernova events, but we see some of them, if they're pointed straight at us, as the long duration gamma ray bursts. Now, if we take a little survey now that we've got Swift up there and been collecting data for 15 years or so, roughly 1 gamma ray burst every day is being picked up. And the majority of them are from the other side of the universe, from vast distances, sort of 6 to 9 billion light years away. And so they were probably happening that far back in time as well. And the modern universe perhaps doesn't seem to build quite as many giant stars, and therefore we don't see quite so many in our backyard. But the Milky Way is nevertheless expected to produce a GRB on a frequency of once every 10,000 to 1 million years. I know that's a big range, but we're not entirely sure just how many of them there will be. And of course, only a small percentage will be aimed at us. So the question therefore is, would it hurt us if we were hit by them? And indeed, have we any evidence of having been hit by a GRB in the past from a local one, rather than one that we can observe from a very safe distance of halfway across the universe? And digging into this one, well, it turns out the answer is probably yes, on more than one occasion, and quite recently too. The year 1775 showed a very striking spike in the abundance of carbon isotope 14 with 2 extra neutrons. And this was detected in trees in Japan, and Japanese pine trees in particular, but then followed up in Australia with cedar trees and other observations elsewhere, as you can see on the graph there. So we got quite a lot of data that shows that round about 1775, suddenly something happened that produced a 20-fold increase in the amount of radioactive carbon-14. And we also have recently detected beryllium isotope 10 in core samples from the Antarctic from the same year. Now, that in itself could be down to a number of different explanations, but we have one particular report translated here from the Old English. It says, year of our Lord, Annus Domini 1774, this year the Northumbrians banished their king Ulred from York at Eastertide and chose Ethelred, son of Mull, for their lord, who reigned for 4 winters. This year also appeared in the heavens a red crucifix after sunset. Well, that's probably the supernova, the hypernova, the gamma ray burst itself, visible in the night sky. And if it's visible after sunset in the twilight, then it's evidently probably very, very bright indeed. And as it would have to be if we were correlating the radiocarbon-14 and beryllium-10 data with this. So it's highly probable. Another possible explanation for this data, though, is that we might be looking at a very, very intense solar storm. And maybe that red crucifix thing in the sky was an aurora. But it doesn't sound quite plausible to me. But the correlation between beryllium-10 at the top here and carbon-14 down here and chlorine-36 here all does tend to point maybe to it being a solar event, but we're not quite sure. What we're more certain of is a little bit further back in time, 443.8 million years ago, there was a gamma ray burst somewhere not too far away in our Milky Way, within about 6,000 light years, which caused a mass extinction event on Earth. It mostly affected the creatures that were surface living in the sea, and at this stage there was nothing living on the land anyway. But the deep sea creatures were protected because they were under that thick layer of water, although they weren't completely immune from it because quite a lot of the plankton were wiped out. And of course, those served as the food for some of the deeper creatures. And we definitely again see carbon and oxygen isotope signatures, which really can only point to a gamma ray burst. And so this was the event that marked the end of the Ordovician era and the beginning of the Silurian period. And this was the time of the trilobites and the ammonites and the brachiopods and those sorts of creatures, all before really we got anywhere near modern things like fish or dinosaurs or amphibians. So very ancient creatures indeed. Now, just to getting towards the end now, but here's just an example of a type of star that we need to keep a bit of an eye on. We see some of these stars in our Wednesday night observing sessions. There's one in the middle of the Crescent Nebula, which is one of my targets for this week. And these are hypergiant stars that are in our galaxy, and this particular one, WR, Wolf-Rayet 104, is 8,000 light years away and a potential gamma ray burst candidate when it explodes. These stars are so massive that they've got so hot in their inner regions and are releasing so much energy that they completely puff off and blow away their outer hydrogen layers. That's what you can see as this a sort of planetary nebula imposter here. But the core inside is still cooking away. It's not dying as a white dwarf star, as would be the case for a normal planetary nebula. Here, the star is an outer layer of helium, pure helium, with helium burning going on in the center, right through to carbon, oxygen, neon, and so on, up to and including iron eventually. And you know, it's probably got 500,000 years to go, this particular star, but we might be wrong. It might be due to collapse next week. It's very, very difficult to tell. Now, we're particularly worried about this one because we're looking down the spin axis. We can tell that because the outflow of the hydrogen envelope is more or less a circle around it. So we're pretty much looking down the spin axis. With any luck, the magnetic axis will be offset, and with any luck, if it does blow up as a gamma ray burst, it will miss us. But we are watching these Wolf-Rayet stars in the Milky Way with some interest. And just recently, we've started to discover ultra-long gamma ray bursts, which we don't really understand. They could be probably something to do with black holes feeding, but perhaps black holes feeding on entire stars, wolfing them down in one go, but we don't really know. And this particular one that's referred to here, GRB 101225A, is known as the Christmas burst because it occurred near Christmas a couple of years ago, and this was detected again by satellite, and its overall duration of the total event was 7 hours, but with a peak of 28 minutes. And so it's really quite a long tail on this event. So something rather interesting was happening. And so that's the story of everything there is to know about gamma ray bursts. I hope you found that educational. I've just got a couple of extra slides, as we've got time, to mention about other ways in which particularly massive stars can die. So we'll go past the end. First of all, for the modest sized stars between 10.5 and about 20 solar masses, these die to form neutron stars. Neutron stars about the size of a city. Here's New York, Manhattan Island. Here's a neutron star for scale. And these are formed by what's called electron capture. So the protons in the nuclei capture electrons and are converted. 1 plus and 1 minus makes a neutral particle, a neutron, N, and they give off a surge of neutrinos, which are marked by the Greek symbol nu, E there. So that's the process by which modest size stars that form neutron stars die. Now, we've talked about the core collapse of the giant stars and the way that they can sometimes they go and form a neutron star, and then the neutron star becomes overloaded and it goes on to form a black hole. Other times they go straight to a black hole. And one of the things that can happen in particularly enormous hypergiant stars is that the gamma ray radiation in the core can become so intense that it has enough energy in each photon to start creating matter-antimatter pairs in the form of electrons and antimatter electrons called positrons. Now, when it does that, when that limit is reached, that it gets hot enough that the gamma rays have that much energy, suddenly they start forming these electron-positron pairs, and it suddenly converts a whole lot of energy into a whole lot of mass. And that effectively cools the core of the star very quickly. meaning it can then not resist the pressure anymore, and so it can crush right down in an implosion event there. And so it can happen to these stars before they get to the point of running out of fuel. If they're large enough, then they can detonate as a supernova through this pair instability process early, even without reaching the iron stage. And this tends to happen to the blue supergiant stars. They don't undergo the onion layer structure. They tend to blow up as pair instability supernovae instead. And usually that results in a black hole, but it can form a neutron star temporarily. Usually the neutron star then acquires too much mass and collapses. But it's a complication in terms of looking at what happens with these very large stars. And that's true all the way up to 130 solar masses. Now, there aren't very many stars over that, but over 130 solar masses, then the process runs to completion without leaving a remnant. And so it's the hypernova is so powerful it destroys the whole star and leaves nothing, no neutron star and no black hole either. So it's a different process. And for the really large stars, the largest ones we see that are about 250 solar masses, there is a very curious process that can occur called photo disintegration in the core. So they get so hot and again produce very, very energetic gamma rays that as they start trying to build their iron core ready for a core collapse hypernova detonation, process described in this little chart here, the iron nucleus gets hit by a gamma ray and is smashed into 13 helium nuclei and 4 neutrons. And then even the helium nuclei can be smashed back to protons and neutrons. And this actually reverses all the work that the star had done in terms of building up through the stages of nuclear fusion from hydrogen to helium on through all the other steps all the way to iron. But suddenly the process gets reversed. The gamma rays become so intense they destroy all these nuclei right back to their original components. Now when that happens in these cores, again, it's hopefully obvious that it's consuming energy to do so, because when we built the heavy nuclei up, we released energy, and so to smash them down consumes energy. We end up back where we started, and the gamma rays have fueled the destruction back down to the original protons. And so suddenly again the core of the supernova cools off very, very quickly, and then can't sustain the pressure on the outer layers, and so it triggers a runaway collapse. And usually when this happens, the runaway collapse goes 100% and the star just vanishes in an enormous flash and leaves no noticeable remnant behind it. And so these very large stars have these couple of extra bizarre ways of dying that no one ever tells you about, but in the context of hypernovae and gamma ray bursts, I thought I'd throw them in.